Welcome to video lecture B5. This one is on vector space bases. I'll be your educationalist, Tom Roby, and here are the outline and objectives. We'd like to generalize the notion of linear independence to general vector spaces. This won't actually be very different from what we've already seen in R to the n. And we'll define a basis of a vector space, or a vector subspace, really. And we'll prove that any spanning set for a vector subspace H actually contains a basis for H. So that means, like in one of the examples from last time, where we had 3 vectors, but we really only needed 2 to span R2, we can always do that kind of thing and eliminate vectors until we are left with a minimal possible efficient spanning set, which is what a basis is. Okay, so here's the first definition. And I just cut and pasted this definition actually from the previous video lecture, E12 or something, where this happened. So a set of vectors, v1 through vp, is called linearly independent if the vector equation, x1 v1 plus dot 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 plus xp vp equals 0, has only the trivial solution. In other words, if you made those v's the columns of a matrix, then that matrix would only have a trivial null space. It would only have the trivial solution to the homogeneous set of equations. So all the xi's are 0. We'll call a set linearly dependent, on the other hand, if we can find a non-trivial collection of c sub i's so that c1 v1 plus dot dot cp vp is equal to 0. Okay, so that would mean that vector c1 through cp would be in the null space and would be a non-trivial element of the null space. All right, so this is, if I have such a thing, it's called a linear dependence relation, and this is really exactly the same as the definition in R to the n, because we frame things in such a way that this notion only depends on things that every vector space has, namely vector addition and scalar multiplication. Okay. So here's a proposition. Maybe you can help me fill out the last word here. A set containing the 0 vector is linearly dependent. If you got dependent, you're right. And that's just because, right, if I have the 0 vector, if one of these vi, say vp was 0, then I could make cp be 1 or 3 or 17 or something, and then all the other ci's would be 0, but because this one was non-zero, I'd have a non-zero linear combination, linear dependence relation. So I can't have the 0 vector. And if I've got a set of just 2 vectors, that'll be linearly dependent if and only if one of the vectors is a multiple of the other. If they're both non-zero, then each one has to be a scalar multiple of the other. But one of them could be 0, and you don't know which one. But basically, it's easy to check whether a set of 2 vectors is linearly dependent or not. Okay, so the proofs of these things are exactly the same as they were back when we did them in the first time, so I'm not going to repeat them here. But here's the fundamental definition, and we'll be spending a lot of time with this definition, because bases are basically the kinds of coordinate systems. They're the way we view how a vector space, it's how we understand the vector spaces through a given basis. And sometimes when there's more than one basis, we can pick the one that's most convenient, most elegant, that helps us understand it best for whatever purpose we currently have. So suppose I've got H as some subspace of a vector space V. It could be the whole vector space V. That would be fine. That's one possibility. And I want to have my index set B. So I'm really thinking about these vectors as coming in a certain order. Usually for bases, that's the way to do it. And in fact, it would be better if most books defined a basis actually to be an ordered tuple rather than a set, which is typically unordered. So this is kind of an ordered set, and it's useful to keep that in mind as you're going through these, because some things will make more sense if you think of them that way. All right, but so what is a basis? A basis is a set of vectors which is linearly independent and spans H. Right? So that'll be a basis of H. So the idea is that I can write any vector in H as a linear combination, and if the basis is, not only can I write it as a linear combination, but I can do it in a unique way. Right? And that's what a basis is going to give us. Okay, so let's look at some examples. So for each of the following subsets, I'll give you brief pauses. You can pause the video if you want longer ones, to classify each of the following sets as being either linearly independent or dependent. So for the first one, well, so this is an R2 by 2, right? So my elements are 2 by 2 matrices, but they're not representing linear transformations here. They're representing vectors. So I think of each of these as like a vector with 4 entries. And this is 3 times that one, right? By the way multiplication works. So since multiplication is just coordinate-wise. So since this is 3 times that, it's some scalar multiple of it. And so those two, so that set is linearly dependent. Okay. For this one, how about this set of 4 vectors in R2 cross 2? Well, it's clear that I can write A, B, C, D as A times this vector plus B times this plus C times this plus D times that, right? So it definitely spans all 2 by 2 matrices. On the other hand, it's going to be linearly independent, right? Because if I tried to write a linear combination of these guys, A times this plus B times this plus C times this plus D times that equals 0, I would end up just getting the matrix A, B, C, D equals 0, 0, 0, 0. And so all of those A, B, C, and D would have to be 0. Okay, so 2 is kind of the classic basis. It's the easiest basis to understand, and it's really the analog of the standard basis EI for R to the n. All right, how about this set of vectors in P3? So now things get a little bit more interesting. So why should, is this linearly dependent or independent? And, well, suppose we wanted to try to write, for 3, suppose we wanted to try to write a linear combination. So suppose I had, let me just, instead of using C1, C2, 3, let me just use A, B, and C as my scalars because it's a little bit easier. So if I have A times 2 plus t cubed plus B times 1 minus 3t plus t squared plus C times 1 plus 2t, and I suppose that's equal to 0, by which I mean the 0 polynomial, right? So what can I conclude? Can I conclude that A, B, and C are 0? That's what I want to conclude. Well, what's interesting to think about here is that this is the only one with a cubic term, right? So when I expand this out, I'll get A times t cubed plus some lower order terms. In fact, I'll get A times t cubed, and then I'll get the 2a that I'll add into the constant term. And now here I'll get plus b times t squared plus, minus 3bt and plus a b, but those are lower order terms. So everything else is lower order terms plus lower order equals 0. But these are the t cubed and b squared terms. But of course, a polynomial can only be 0 if all of the coefficients are 0. So that means that a equals 0 and b equals 0. Okay? So now that means we're just left with up here. So now we're left with c times 1 plus 2t equals 0. But that means that c plus 2tc equals 0. The only way that can happen is if c equals 0. Okay? So we've shown, by supposing that we had a linear dependence relation with coefficients a, b, and c, and showing that they all had to be 0, so we conclude that this set 3 is linearly independent. Now, on the other hand, there's the question of, does it span all of P3? So later on, we'll see a simple argument why this couldn't span P3, because P3 actually has 1t, t squared, t cubed. It's actually a 4-dimensional vector space, and I only have 3 vectors here. But we haven't defined dimension yet, and that's, of course, what we're shooting towards. So how can I give a naive proof that this doesn't span? Well, let's see. I thought I had a simple way to do this. So I claim that I can't get t cubed as a linear combination of these things. So let's see why that's true. Right, so suppose I could get, so if t cubed were equal to a times 2 plus t cubed plus b times 1 minus 3t plus t squared plus c times 1 plus 2t, right? If t cubed were in the span of these three vectors, what would that mean? Well, I'd have to have that a was equal to 1, right? Because that's the only t cubed term. So a would have to be equal to 1, and when I subtract the t cubed from each side, I get that 0 was equal to 2a plus b times 1 minus 3t plus t squared plus c times 1 plus 2t. Now the only t squared anywhere is bt squared. There's nothing here or here to cancel it out, so therefore b has to be equal to 0. And now once b is equal to 0, I can forget about this. And this is the only coefficient of t is 2ct, so that has to be equal to 0. And so right, and so then a would have to be, a is equal to 1, and so we end up with 0 equals 2, which can't happen. Okay, so that's how you can show that something is not in the span. So t cubed is not in the span. But again, we'll get more efficient ways to deal with this once we really understand bases and dimension. Okay, here are two more that should have been separated by a pause, but let's look at 4 first. So how about, I'm looking at continuous functions from minus pi to pi. Okay, that could be 0, 1, it doesn't really matter. But so I've got sine squared of x, cosine squared of x, and cosine 2x. Are those linearly dependent or independent? Well, we know that if you remember your trig, you remember that cosine of 2x is actually equal to cosine squared x minus sine squared x. Okay, so that means that cosine 2x minus cosine squared x plus sine squared x is equal to 0. So that's a linear dependence relation. Okay, so therefore they're dependent. So it's not linearly independent. And now finally, let's look at the columns of this matrix here. So we've got the columns of the matrix, 3, 0, 0, 0, minus 4, minus 2, 0, 0, and so on. They're in R to the 4. What can we say? Well, here's where you want to use the power of the invertible matrix theorem. So this matrix is clearly invertible. Do you see why? Well, what's the determinant of the matrix? Right? This is a triangular matrix, so the determinant is just the product of these diagonal entries, which is negative 18. That's not 0, therefore it's an invertible matrix. By the invertible matrix theorem, the columns are linearly independent and they span R to the 4. So, well, I guess we haven't gotten there yet, but at least they're linearly independent. Right, and so then the last question is, which of these are bases? Right, and so since I just said that these are linearly independent, but they also span by the invertible matrix theorem, so 5 is definitely a basis. This is linearly dependent, so it can't be a basis. This one was linearly independent, but it didn't span. So if it's linearly independent but it didn't span, it can't be a basis. These guys we saw were linearly independent and span, so they are a basis. And then these were linearly dependent. So we have not a basis, basis, not a basis, not a basis, basis for these 5 examples. All right, so now that we've looked at a bunch of examples, let's look a little bit at the theory. Suppose I've got an index set of at least 2 vectors, v1 through vp. Then it's linearly dependent if and only if at least one vector is a linear combination of the others. Okay? So, in fact, if v1 is not 0, then I can always find some j bigger than 2. So, I check, is v2 a multiple of v1? No. Is v3 a linear combination of v1 and v2? Yes or no. Is v4 a linear combination of v1, v2, and v3? At some point, if they are linearly dependent, I'll find some Vj, which can be written as a linear combination of the previous ones. Okay, so that's just a helpful thing for doing certain proofs. And we already proved this in video lecture E12 for r to the n. And again, the proof is no different for any vector space, because it only depended on things that all vector spaces have. Okay, so now let's look at the following spanning set theorem. So suppose that I've got a set of vectors, p vectors, and they span a subspace H within some other vector space V. So suppose that some Vk is a linear combination of the other V sub i's. So when I get rid of V sub k, that's what this S minus Vk means. This is set difference. So S prime is just the set S where I've taken Vk out of it. Okay, so I have one fewer vector. So if I can write Vk as a linear combination of the ones in here, then S prime also spans H. In other words, if I could write one thing as a linear combination of the others, then I didn't actually need it in order to span my vector space H. And the consequence of that is that if I've got a non-zero subspace, then there's, and it's the span of S, then there's some subset of S that's actually a basis for that subspace. Okay, and so here's the argument. So first of all, I said Vk is a linear combination, but I could always rearrange the order of these and make Vk be the last one Vp, and that's just a little easier to do that for writing things down. So without loss of generality, that's what log means. You'll see it a lot if you keep going in math. Without loss of generality, assume that Vk is the last one Vp, right? So then by assumption, I can write Vp as a linear combination of these other ones, V1 through Vp minus 1. Now if x is in the span of S, what does that mean? X is in H, then it's in the span of S by definition, by assumption. So then I can write X as this linear combination of all the V's, V1 through Vp. Okay? But now I know that I can write Vp as a linear combination of the other V sub i's. So I'll just plug that in. So just plug in A1 V1 plus dot 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 plus AP minus 1 Vp minus 1 in for this right here. And when you do that, you'll see that what do you get? Well, you'll get Cp times A1 V1 plus dot 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 plus Cp times AP minus 1 Vp minus 1. Now you just combine each of those terms with the ones that you've got here. You already have C1 V1s, but now you'll add to it Cp times A1 V1s. So you'll have C1 plus Cp times A1 V1s, and so forth. Here you'll have Cp minus 1 plus Cp AP minus 1, Vp minus is the scalar times Vp minus 1. And that's clearly in the span of S prime. So I've taken anything that's in H, and I'm able to write it in the span of not just S, but in S when I've deleted this last vector. Okay? So that's what shows that getting rid of that vector doesn't hurt me if it's already a linear combination of some of the other vectors. Okay? So then the last proof here is that, well, some subset of H is a basis for H. So why is that true? Well, okay, if it's not, I know it spans, right? I know that S spans, so the only question is it linearly independent. If it's not, it's linearly dependent, then that means I can find some VI that I can write as a linear combination of the other ones. Okay? But when I do that, but if I can do that, that means I can get rid of it, right? And I can delete it and I get S prime. So that's a smaller set of vectors, and then I say, okay, is this smaller set of vectors linearly independent? If it is, good, then I have a basis. If not, well, then it's linearly dependent, and there must be some vector that I can write as a linear combination of the other ones. So then I apply this argument again, get rid of that vector, and just by doing this over and over again, eventually I have to get to the point where I still have, at each point I still have a spanning set of vectors, and at some point it has to become linearly independent, right? Because eventually I'll get down to like one vector. I know there's at least one non-zero vector in here because this is not equal to the zero subspace. Okay? So that's it. That's the spanning set theorem, and it's very useful. It means that if you write down any spanning set, no matter what, that you don't need to like do anything complicated to find a basis. You can just get rid of the chaff. Get rid of the people who aren't pulling, the vectors that aren't pulling their weight, and just any of those that could be replaced by some linear combination of your other vectors, you get rid of those, and you just keep doing that, and eventually you'll get a basis for your vector subspace. So that's linear independence in theory. So, and that's it for video lecture B5. Thank you for your kind attention.